Hi everyone. In the last video, we saw important classification matrices. Now let's move toward modern CNN architecture tutorial. I'll open the Colab and let's see how we have used it and coded it in our Colab. I'll explain it cell by cell to you. Um, let's start. So in the first markdown cell, I'm explaining the modern CNN architecture from ResNet to EfficientNet. Basically, the evaluation from 2012 to 2021. ResNet was in 2015, EfficientNet in 2019. How we evolved from this to this, we'll see how it evolved and how to use it. So first we'll do the setup and imports. We'll do all the files import, and then we will set up some beautiful plots, standards and device configurations and reproducibility. Once we are done, we will start with our chapter 1, that is the vanishing gradient problem. Why deeper isn't always better? Before 2015, the training very deep networks was nearly impossible. The problem was the math behind the vanishing gradients. When we have a layer 1, layer 2 and n number of layers, the gradient was very small, that is vanishing, and then it got increased and it got lost. So that was the vanishing gradient problem. Let's demonstrate it. We have created a deep network to demonstrate the vanishing gradients, and then we have measure gradient norms at each layer. We have defined this function which will measure the gradient norms at each layer during the forward pass, backward pass, and it will collect the gradient norms, and it will compare the sigmoid versus ReLU here and visualize it. We will do the visualization and the log scale printout. So here, see, we are visualizing our gradient demo. We can see uh, the sigmoid vanishing uh, across the layers, and so that's why we move to chapter 2, that is the ResNet, the residual revolution. So why does it works? It is easily learned to identify gradient highway. Gradient flows directly through skip connection and feature reuse. Later layers can access their earlier features. So let's see the basic residual block first. So this is the structure, basic residual block structure: convolution, then batch norm, ReLU, convolution, and then batch norm. And we skip the connection and then again ReLU. So this is the init function where we have defined the main path, the skip connection strategy here, and then we will define the forward function where we have our main path and we will skip the connection plus residual here. That is the main innovation, and then we will do the final activation. We will test the block here, and then we will test with the downsampling, and we will print our output. So this is our output for the same. Moving to the neck, that is bottleneck residual block. So bottleneck residual block used in ResNet, and it uses 1 cross 1 convolution to reduce and restore the dimensions. Uh, First we have the convolution 1 cross 164 ch that squeeze to a fewer channel, and then we have convolution 3 cross 3, that is the main computation, and then we have convolution 1 cross 1 with 256 ch that is expanded and back to the original. So let's see how to implement it. So we have expansion as 4, and we have defined here 1 cross 1 squeeze, 3 cross 3 main convolution, and then again 1 cross 1 expand convolution. And this is our shortcut that we have defined here. We have defined the forward function here. We'll compare the parameter counts here, and for 256 input channels we'll call the basic residual blocks and the bottleneck functions, and we will compare the outputs. So we can see the outputs, and we can see the basic block has this many parameters while the bottleneck has this many parameters, and bottleneck uses 6% of the parameters, and this is why ResNet 50 plus uses the bottleneck blocks. So now we will see the complete ResNet implementation. A complete ResNet implementation architecture looks like input passed to a convolution of 7 class 7, and then pass to a max pool of 3 cross 3. Stage 1 is the blocks, then stage 2 blocks, stage 3, stage 4, and then a global average pool of all. So this is how we have defined it. Now let's see it in the code. So we have it in a init function here. We have this initial convolution defined here. We have the residual stages set here. We have defined the classifier, the initial weight. We make the layers. We define the make layer function here, where we are doing it for every stride in the strides, and then we will initialize the weights here. We'll define the forward function here, where we will have the stem, the residual stages, and the classifier defined. Then we will define the resonate variants of 18, 34, 50, 101, 152 different resonates, and then we will compare the variants in the family with all the resonates, and we will run it for all the variants, and we'll see the output. So we can see different resonates, different parameters, and different block type was used. We'll see the gradient flow in the resonate. So gradient flow plane versus residual. So let's see. This is the plane block without skipping the connection we have defined, and this is the residual block with skip connection we have defined. And then we are comparing the gradient flow from both and plotting it, visualizing it. So let's see. This is the plane residual versus this is the gradient flow log scale. Now the next is the advanced building block, modern innovations in the CNN block. So we have the AC block, MB convolution, and the ConNetX block, and what is the key innovation behind them and where they are used in. These things we have mentioned here. First is the squeeze and excitation block. So in this we have this function defined where we are doing this squeeze and excitation block. It learns to weight channels based on their importance. So suppose we have this input, we have a global average pool, it will squeeze it, then it will reduce it, pass it to the ReLU function, and then it will again expand it back to the C, and it will provide the excitation using the sigmoid, provide the channel weight, and then it will recalibrate the input. And let's and this in this notebook we'll see how channels are important, how we will do it. So we are defining here the init function where we are defining the mid channels, squeeze, excitations, all the values. We'll define a forward pass in which we are squeezing the global average pooling, we are applying the excitation, and then we are recalibrating the scale channels, and then we will test the SE block on that, and we will see the input, output, and the parameters uh, in the output. So this is what we are seeing: input, output, and the parameters here. Moving toward the next is the mobile inverted bottleneck, MBConf. So in mobile inverted bottleneck, it is inverted because it expands and then compresses. So let's see in this flow. First we have input C channels. We expand it into 1 cross 1 convolution, C into expand, and then we do spatial filtering, and then the AC block is optional, and then we again project it back to the output. So this is the key innovation behind it. So let's see, we will do the expansion, and then we will do the depth wise convolution, we will do the AC block part, and then we will do the projection, that is no activation and linear bottleneck. We will test the MB convolution here, and then we will compare it with the standard convolution, and we will print the output. So this is the MB convolution block, and this is the comparison with the standard. We can see MB convolution block had 17,000 something parameters, and it is having 18,000 something parameters. So depth wise separables is much more efficient. Move toward the let's move toward the efficient net compound scaling. So efficient net is this is what we have here. We have different stages defined, and we will do scaling coefficients with B0 to B7. So this is the variance and the depth and dropouts we have printed in the output. We'll use pretend efficient net, and we will see how it works. We will load the models efficient net B0 and efficient net B4, and we will count the parameters, we will compare b0 and b4, and we will print the output. We can see the output of efficient at b0 and b4. Now here we will see transfer learning. Training from scratch requires millions of images, expensive GPU. Transferring learning uses pre-trained models as a starting point, and we don't have to do it from the scratch. So we will create a transfer model here. Create a model for transfer learning. Steps is, first is the load a pre-trained model, replace the classifier head, and optionally freeze the backbone. So here we are loading a pre-trained model. If base model is equals to resonant 18, 50, or whatever model we want to choose, and then we will freeze the backbone here. So we are creating the model, we are trying to train them, and we'll see how the actual it is trainable or not, and it works 100%. So next is the data preparation for transfer learning. ImageNet statistics we are going to use. These are the pre-trained models, expect this. So these are the training transformers, and we will resize the smaller edges, we will do the random cropping, we will validate the transformations, we will center crop, and then we will print it. And these are the key points for transfer learning transformations that we have to keep in mind. Next is load Cypher 10 for transfer learning. So for transfer learning demo, we will use Cypher 10 resize to 224 cross 224. In practice, we would use our own data set. So this is the Cypher train transformers. This is the Cypher validation transformers. We are loading the Cypher data set. We are training and testing data set we are defining here, and then we will use the subset for faster trainings, and we can see the training samples and the testing samples are here. Now we will see the fine-tuning strategies, the advanced techniques for better results. First is the discriminative learning rates, and for this we create the parameter groups with discriminative learning rates. Earlier layer gets lower learning rates, and the later layer gets the higher learning rate. We can see we have defined here ResNet models. The classifier get best learning rate. Earlier layers get the lower learning rates because of this loop. And here we are creating a transfer model ResNet 18, and we are running it through the layers, and we will see the learning rates here. Now we'll see a complete transfer learning training. We have defined this train model here. We'll only optimize the trainable parameters. For each epoch we will be doing this training and validation part, and once that is done we will print the history. And this is here we will compare the approaches. First is the feature extraction, second is the fine tuning all layer, and third is the training from scratch. And we will compare all these three, and we can see the difference between training and validations, and we will visualize the comparison of all the three methods. We can see there is a huge difference between validation accuracy and epochs for all, and where the fine tuning works the best for the final validation accuracy. And this is the summary of what we have done. This is the quick cheat sheet telling what we have done till now. So that's all for this collab. Thank you so much.